Ask everyone to join the class. Okay, I'm sharing my screen, okay?
Exact same problem, only it was pinned with ball and socket joints at each end. This time we're talking about fixed ends, and that's going to Alright guys, welcome back. In this video we are doing another example on column buckling. In this case we have a three-dimensional column that has a fixed connection at both ends. So very similar to the last video. If you watched it, we had basically this exact same problem, only it was pinned with ball and socket joints at each end. This time we're talking about fixed ends, and that's going to change our effective length that we're dealing with. Now if you remember from a couple videos ago, we had been talking about this stuff, our different situations where we had like pin, fixed end, and free end, a fixed end with a pin end, and a fixed end with a fixed end. Well, this is the situation that we have in this video. So we're saying that means our effective length is going to be equal. Alright guys, welcome back. In this video we're doing another example on column
Screen is not
buckling.
visible.
In this case we
Okay,
have
let me
a
share once again.
three-dimensional column that has fixed end with a pin end and a fixed end with. Alright guys, welcome back in this video. We're going to do
Now it is
another
okay?
example on column buckling.
Audible?
In this case, we
Video?
have a
And
three-dimensional
screen is
column that
visible?
has a fixed connection at both ends. So very similar to the last video. If you watched it, we had
Okay,
basically
okay.
this
Okay,
exact
start
same problem.
from the beginning, okay? So this problem
Alright
is
guys, welcome
different.
back in this video. We are doing another example on column buckling.
Both
In
hands
this
will
case, we
do.
have a
And
three-dimensional
fixed here,
column
okay?
that has a fixed connection at both ends. So very similar to the last video. If you watched it, we had basically this exact same problem, only it was pinned with ball and socket joints at each end. This time we're talking about fixed ends, and that's going to change our effective length that we're dealing with. Now if you remember from a couple videos ago, we had been talking about this stuff, or different situations where we had like pin, fixed end, and free end, a fixed end with a pin end, and a fixed end with a fixed end. Well, this is the situation that we have here in this video. So we're saying that that means that our effective length is going to be equal to 0.5 times the actual length. And so in this case, our actual length is 3 meters, and so our effective length, maybe let's not draw an equal sign, let's draw an arrow. So we have our effective length is going to be equal to 0.5 L, so that's 1.5 meters. Alright, and that is coming directly from that last, not that last video, but a couple videos ago where we talked about that. Okay, so when we start talking about this for buckling, is this column can, as a rectangular column, it can buckle in two different directions or planes basically. It can buckle in the YZ plane, basically going out that way or coming this way, and it can buckle in the XZ plane, so basically kind of going into the page like that or out of the page like this. So we need to check what the critical load is for each possible direction it can buckle in. And then from there we can use the factor of safety to determine the allowable load, and then after we'll also check to make sure that this thing, to see if it's yielding before it's buckling or whatever. Alright, so the formula that we need to use, just like the last couple of videos, was P is equal to P crit is equal to pi squared EI over L E squared, right? The effective length squared. So in this case, we do need to identify the moment of inertia that we're going to be using in each direction. So for buckling in the YZ plane, just like the last video, we need to find the moment of inertia about the y-axis. And then for buckling in the XZ plane, so this way, we need to find the moment of inertia about the x-axis. And we did calculate those in the last video, so we'll just write them right here. And then we want to use each of these when we calculate for buckling in each of the planes. So let's take a look at buckling in the YZ plane first. So we want to figure out what the P critical is in order for that buckling to happen. So then we're going to have to use the subscript here for I, Y, moment of inertia about the y-axis when we're dealing with buckling going like that. Alright, so when we have all of these values, we have the effective length, we have the moment of inertia, we have E, we have pi, obviously. So we're going to find that the P critical in the YZ direction is 23.4 kilonewtons. And now we want to repeat the process to find the critical load for buckling in the XZ axis. So let's throw in some subscripts here. XZ, and this time we need to be using the moment of inertia about the x-axis, so we have subscript x up here. Alright, so when we go and plug in all of those numbers, we're going to find that the critical load for buckling in the XZ axis is 93.6 kilonewtons. So now what we do is we select the smaller load as our actual critical load, because obviously if you surpass the smaller load to get up to the bigger load, you already would have buckled in that direction or in that plane. So what we do is we take this, and if we're asked to find the allowable load for buckling with some safety factor, we can do that. We just take our factor of safety, which is equal to the ultimate load over the allowable load. So we can just rearrange that so we get our allowable load is going to be equal to 23.4 kilonewtons over a factor of safety, which is 2.5. Alright, and that works out to be 9.36 kilonewtons. So with a factor of safety of 2.5, then we can safely support this compressive load here of 9.36 kilonewtons. Now, something that we should do is just like exactly like we talked about in the last video, is we should check that that we're not at risk of yielding with this applied load. So let's just give ourselves a little bit more space down here. We know that the yield stress for this material in this problem is 250 megapascals, and we also know that stress is equal to force divided by area. So we have P over A, and in this case for yield stress, that is our ultimate strength, or our ultimate load here. So we can say Py or P ultimate, whatever. It's a load that's going to make the material yield. So what we do is we just have to rearrange this to solve for Py. So we know that the area up here, the cross-sectional area, is 800 millimeters squared. So we get 250 times 10 to the 6 newtons per meter squared. That's megapascals, times our area, which is just 800 times 10 to the negative 6 meters squared, and that's going to be equal to 200,000 newtons, which is 200 kilonewtons. And basically this material, when we look at this material will yield when we apply 200 kilonewtons to this exact column. And that's way more than if we applied only 23.4 and it's going to buckle. So it's safe to say that this column will buckle in the YZ direction or plane before it even buckles in the XZ plane and before it yields due to compression. What's up, guys? Welcome back. In this video we are doing example number 4 of
Video is
column
visible?
buckling. So in this
Is it visible? Is the screen is visible? Okay.
example we have a rectangular column that's fixed at one end and it's pinned at the other end, but this pin only works in one direction. Basically it's for buckling in the YZ plane, the column sees this connection as a pin, but for buckling in the XZ plane, there's really nothing stopping it from swinging out if it was to buckle, so the column sees this as just being free to buckle in the XZ plane. So when we look at, if we go back to a couple videos ago, as always, we had these situations up here. So in the case of a fixed, let's do a fixed connection at the bottom and a pin at the other end, then the effective length that we're going to be using in our peak critical formula is 0.7 times the actual length of that column. And then for a column that's fixed on one end and free at the other end, we're using effective length of 2 times the actual length. So depending on which way we're considering buckling to go in, we're going to have to use each of those. So maybe let's write those out. We'll just say that we have our effective length for the YZ plane. This is going to be where we have a fixed pin connection, so that will be equal to 0.7 L, and 0.7 times 3 there is just 2.1 meters. Alright, now our effective length that we're going to be using in the XZ plane is was 2L for the fixed and free connection, and so just 2 times, so we can write that 2L, so that's just going to be equal to 6 meters. Alright, let's go and grab this expression up here. We are going to need the moments of inertia about the x-axis and the y-axis, and we've already calculated those in previous videos for this exact cross-section, so I won't bore you with those. And we're just going to plug them into the p-critical expression. So let's just give us, we have to do this for each possible direction for buckling. So let's check the YZ plane first, and that's going to give us the subscript IY, because it'll be buckling in this way or that way. So basically, if from the top-down view, it's about the y-axis there is the moment of inertia that we're concerned about. So when we plug all that in, we just get it to be equal to 12 kilonewtons. And now we just want to check for buckling in the XZ plane. So let's just bring this down here, and we'll add in our subscripts. So we're looking for P critical in the XZ plane, which means we're dealing with the moment of inertia about the x-axis. And then again, this is the effective length for the XZ plane. Alright, so when we just plug in all the values that we already have, we find that to be 5.9 kilonewtons. And 5.9 is smaller than 12, so when we look at this, the actual P critical that we're going to get for this column is 5.9 kilonewtons. We're going to be getting buckling in the XZ plane before we get buckling in the YZ plane. The other thing that we can do here is we can just check the allowable load if we want, based on the factor of safety. So let's just write it down here. We have factor of safety is equal to the ultimate load over the allowable load. So if we just rearrange for the allowable load, we will just get the ultimate load, which is 5.9 kilonewtons, divided by our factor of safety, which was 2.5. And that's going to give us an allowable load for this column of 2.95 kilonewtons. This is equal to P allowable. Alright, so let's throw a box around that one as well. That's our allowable load. And the last thing that we want to do here is we just want to check to make sure that the column doesn't yield before it buckles. We've been doing this in the previous videos, so all we do is we know that our yield stress is equal to basically just the force over area, and that force is the force that would cause this material to yield. So if we just rearrange for P, we're going to get our yield stress, which is 250, so we have 250 times 10 to the 6 newtons per meter squared, times 800, well this actually, I should write it up here, the area is equal to 20 times 40, so that's 800 millimeters squared. So in units of meter squared, that's just 800 times 10 to the minus 6 meters squared. So if you just multiply those two together, we're going to find that the force is 200,000 newtons, or in kilonewtons, that's just 200 kilonewtons. So 200 kilonewtons is way bigger than 5.9 kilonewtons, and it makes sense. This is an extremely slender column. When we're looking at this, it's only 2 centimeters by 4 centimeters in its cross-sectional area, or cross-sectional dimensions, and it's 3 meters long. So no wonder this thing is going to buckle way sooner than it yields.
Okay, so practice these problems in home. Okay, go through the videos and solve the same problem by yourself. Okay, so write your roll numbers in the chat box. Don't leave the class. Okay.